Hello, everyone. My name is Katie Emilio, and I'm an engineer in the Professional Development Department at ACI. I'd like to welcome you to today's webinar, Understanding the ACI 56221 Concrete Repair Code webinar series, Part 4. This is the final part of our 4-part series. We're very glad you're joining us this afternoon. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 2 PDH. Today's presentation is approved by AIA and ICC for 2 learning units. Our webinar this afternoon will delve into considerations for extending the service life of repaired concrete structures. You can see the full description in your course handout, as well as the learning objectives. And now I'd like to introduce Kyle Stanish, our presenter for this afternoon. Kyle is a PhD, structural engineer, professional engineer, and fellow of ACI. He is vice president of the Turney Consulting Group and has over 20 years of experience working as a consulting structural engineer. His work has included durability design for new structures with an extended service life, the evaluation of existing structures, and the design of appropriate repairs and rehabilitation programs to extend the structure's service life. He has worked on a variety of structure types, including bridges, parking structures, plazas, facades, utility tunnels, and miscellaneous structures. He is currently the chair of the American Concrete Institute's Committee 365 on Service Life Prediction, chair of the Durability Subcommittee for the Repair Code, and a member of various ACI committees on repair and durability. And with that, I'd like to pass the presentation to Kyle.
Thanks for that introduction, Katie. Perfect. Thank you very much. So today I'm going to be talking to you this final 4th section of this webinar series on 562, the repair code. So I'm going to be talking about the last portion of the repair code, the last few chapters, including section on durability, section on construction, and section on quality control. And then I'm going to briefly go over an example for one of the guide documents that ACI has produced. So hopefully we're in for a little bit of a ride and we'll kind of see where we're going with things. So first of all, I want to start talking about the durability chapter, which is chapter 8 in 562. And if I've probably seen this flow chart, which is the path through the code, and where, if you look at it, we're down in the lower left corner looking at durability, so coming towards the end. So before I start talking about what's actually in the code, I want to make sure we're all on the same page with what durability is. So durability, it's a very important aspect of your structure, and sometimes you have it and sometimes you don't. But let's get into a definition, and one of my favorite definitions is from ACI 365.1, and that defines the durability as the ability of a material or structure to resist weathering action, chemical attack, abrasion, other conditions of service, and maintain serviceability over specified time or service life. So quickly reading that, there's obviously some differences to what we've been considering in 562 up to this point. We're no longer really worried about loads and stresses and all those fun things you think about as a structural engineer, but more about the effect of the environmental aspects on your structure. And the other thing that's different that doesn't really get discussed very often when you talk about structural design and loads is we're really looking for serviceability over a specified time. So there's a time element to going to durability, that you need to resist these effects, not just today and not just tomorrow, but over some time that you can expect this structure to be around, and that's often not explicitly included. So what, given that as a background, what would you expect? What factors affect durability and durability performance? I've listed a couple here. It's really, the first thing is, well, what type of environment are you in? Depending upon your exposure conditions, the same structure can have a very different durability performance. But also the rest of these are more about the properties of the structure itself, of how you built it, and they're really about mixture portions, mixture proportions, the presence of the reinforcing steel. A lot of the times concrete would work fine, steel would work fine, but when you put them together, there's other things that you need to think about. Detailing, finishing and curing, protection, these kind of ideas. And that's really where this durability chapter, this whole section is pushing you to think about how are we going to develop and specify and design for these proper performance so that we have something that lasts the time you expect it to have. But the first thing you really need to think about, the first way that durability comes about is making sure you have the repairs are compatible with the structure. A lot of what I said on the first slide relates equally well to repairs and new design, where you have a new structure you're starting with. You still should think about the exposure conditions, the detailing, the materials. But what's kind of unique to durability for repairs is that you really almost have these two portions of the structure that have a very different history, very different properties, and they need to work together. So the compatibility is kind of, if you don't have that, you don't have anything as far as durability is concerned. Now, it's important from a structural viewpoint, but it's also very important from a durability viewpoint. So we do spend a lot of time talking about compatibility, and you need to consider compatibility in the code ACI 562. So yeah, this is kind of a summary of how the chapter is laid out. But compatibility of materials is really kind of front and center for a durability consideration. So what do I mean by compatibility? This is kind of more formal definition. It's the capacity of two structures or entities to combine and work together. But really the idea is, you want to make these two one, so they have to have similar properties and similar performance. Or if the properties are different, other properties and other things are considered so that they can still behave together. You're ending up with something that at the end of the day, you're not getting two separate items, but one item that has two parts that are working together. So as you can see on, here, on the left, you have a incompatible materials. Both of them are fine in and of themselves, but they're not working together. Whereas on the right, it's something that is more, there's two items that are, two sections that are working together, and they really become one. And if you don't have compatibility, and particularly dimensional compatibility, this is kind of what you can end up with. This was a repair that obviously didn't behave properly, behave the way they wanted. And what really is happening is the base structure is not compatible and not playing well with the new repairs you have. So the repair, they have different volume change properties. One of them is pulling away from the other. That's the fact that they're have different volume change, but they don't have enough bond, a core bond, to overcome that. And also, that's also leading to things like surface crack tracing and cracking, and just items that go into it that are not allowing the two parts of your structure, your repair material and your original material, to behave well together. So delving into that a little bit deeper, one of the first things that we really should think about when we talk about compatibility from this viewpoint is not strength, but drying shrinkage, really the volume change movement and how that's going to happen together. And we need to realize that the repaired material and the original material are going to have very, very different histories. All concrete shrinks. That's one of those truisms that, if you're working in the concrete field, you should know. It's kind of analogous to all concrete cracks. But what's happened is frequently during a repair scenario, you've got your original structure that's decades old, hopefully, at the time, and it's undergone basically all its shrinkage. When you're applying this new material that, fresh straight out of the box, it still needs to undergo, it still will undergo a lot of shrinkage. So what's happening as a quick refresher, shrinkage occurs when you lose the water in your original concrete after it's set, after it's hardened, but it'll continue to lose water through evaporation or absorption, and you really lead to, and then your concrete wants to get smaller. So you really need to think about that as part of your repair design process, picking the right materials so that they can behave together. That, ideally your new material doesn't shrink way more than your existing concrete. So you often want a low shrinkage material, and these types of things are what the code requires you to think about how these are going to work together. I mean, it does acknowledge, or you should be aware, that no shrinkage is not really a realistic thing, especially for large quantities repairs. So you need to think about bond, which I'll touch on a little bit later, but none of these things happen in isolation. But for compatibility, the first one is, okay, I need to expect this material to shrink. What am I going to do, and how am I going to avoid it? So you can manage it and address it so that you don't end up with things like this, where you've got a whole bunch of cracking in your new material. It's pulling away from the existing concrete. So compatibility in terms of volume change and shrinkage is an important aspect to think about when you're figuring out what your repair material. And the durability chapter of ACI 562 is directing the licensed design professional to consider that effect and how that's going to play out, and how that's going to affect the durability of the repairs. Similarly, equally important from a compatibility viewpoint, and may prevent you from moving away from certain types of materials in some situations, is the stiffness of the concrete, or stiffness of the repair material relative to the stiffness of the original concrete. There's been frequently the tendency is to use a really, really high strength concrete, and that can work really well, but oftentimes it doesn't work really well. And the reason for that is that the modulus, you're not just getting the difference in strength, you're getting differences in elastic modulus. And then the higher strength concrete is stiffer, so it attracts more load, and the amount it participates more in the load sharing is more than the increase in strength. So you can get in the right situation, or probably really the wrong situation. You end up with premature failure of your beautiful high strength, really, important and well made repair material. So this is something you also should be thinking about as the licensed design professional from a durability or performance viewpoint, to get them compatible in the modulus, and then the way that they're going to behave under the loads that will be applied to the structure. And then bond is the other aspect that goes into it, because as I mentioned, they're going to have a different history. They're going to be different materials. Even if you go to a substrate and figure out exactly what was used to produce that concrete and use the same as for your repair material, it's going to have a different history, a different age. So they're going to behave differently. So to get them compatible, that's where the bond comes in. That's where something you need to think about. Okay, that overcomes the differences in properties and compatibility. So bonding is important, or bond is an important aspect. It is touched on in other chapters, but it's also something you need to think about from a durability viewpoint. And these are just listed some of the things, alternate ways or different ways, or that can be used to achieve bond. Preparing your substrate correctly, having it saturated surface dry, using the scrub coat, using bonding agents. And I'm only, from a personal experience viewpoint, I just do want to throw up a flag, something that you should consider out for bonding agents. They can work really, really well, but they can also work really, really poorly if they're not used correctly. So you always, if you are considering a bonding agent, you should be very aware of what the manufacturer's recommendations are for things like open time and cure time prior to application, and compatibility with different materials before they're used, and make sure that the contractor is aware of them and then using them correctly, so that you have the best chance of achieving a successful repair and a successful bond. So that's really, the first step in achieving durability is achieving compatibility. Those are some of the aspects of that you should think about when you're ensuring you have compatibility. But now I want to go on to the next aspect of durability, and probably what more people think about when the word durability is mentioned, is like looking at the degradation that has happened, which is really one of the nice things about a repair program. You have this history of, okay, I'm doing this because of some degradation. I know what's going to happen, so I need to prevent it in the future. So you kind of got that, already you've got a lab experiment, what's going to affect it. But that's something that really needs to be considered by the design professional when a repair is being developed. And I do want to mention that in some ways the durability chapter is different than the remaining chapters of 562. While there is some very prescriptive statements that you have to do this and you have to do that, in many more ways, the philosophy behind the durability chapter is more about, okay, here's all the things that the licensed design professional needs to consider, and that they need to then make sure that you've considered them when you're developing this repair, so that it addresses it properly. And it doesn't always get very prescriptive, like, you need this much cover, or you need to, in this situation, you need to put this type of coating, or this is your properties that you need to have for your repair material. It is more about considering what can happen and giving the design professional a guideline to what you should be considering when you're developing it, but less of a cookbook, but more of a guide down the road. These are things you need to consider. It gives you some guidance in the commentary, but it's more about following a process to achieve the right result, but not prescribing ways to do it, because there are just so many different possibilities. So back onto, after that aside, back onto preventing degradation. When I start talking about durability and service life, one of my favorite kind of charts or visuals that I like to have is this graph here, where you can see, you start at time 0, you have no deterioration, but eventually with time, it gets worse and worse and worse and worse, until for repair aspect, you're looking at, we're at site B, where, hey, there's enough deterioration. It's not necessarily needs to be demoed. You have a lot of value in there, but we want to make the structure better. So most of what people have been talking about up to this point is really going from B to B prime, so that reduction of deterioration. How can we fix what's there, and how do we know that it's structurally sound? And don't get me wrong, super, super important. It's first because it is the first importance. There's no point in doing a structural repair that doesn't meet the structural requirements. But the durability chapter talks less about that than what happens after that repair. And so the idea behind the durability chapter is more about slowing that future rate of deterioration. So that purple line off to the right, that dashed line, or how we want to get that as shallow as possible, so we're not, in the same place we are now in a very, very short period of time. So this is what, if you want to keep that in mind as I go through, the objective here isn't making things better. That's done, elsewhere, super important, but it's how do we push this out, and how do we slow future deterioration rates? To do that, we often need to figure out what the cause, like, okay, well, what is causing that future degradation, that future deterioration? What is damaging our structure? And, as I mentioned, in some ways it's really easy to figure out. It's like, hey, we've got, we have a history with the structure that's caused the spall. Well, what is it? Well, we can, we know that it's corrosion. We know that, so you look for sources of corrosion, de-icing salts, away you go. We need to avoid that. So those are all, that's a lot of good information and helps you think about what you need for durability. But it's equally important to remember, hey, what am I doing here? Am I going to, maybe what was originally there was very durable, and this deterioration mechanism, you need to, but that doesn't, so we're not seeing any signs of it. That doesn't mean you need to ignore it for the repairs. Like, for example, if you have a structure not solid, not affected by alkali aggregate reaction because the right aggregates were used, that doesn't mean you can ignore using the right aggregates for your repair. So all these things, the potential deterioration mechanism as the ones you've experienced, need to be considered. Obviously the ones that are more important and the ones that are usually front and center in your mind are the ones that are motivating the repair, if that's the case. And there are a lot of different degradation mechanisms. Looking at mechanical impacts, abrasion, things like that. So chemical, like I mentioned, alkali aggregate reaction, sulfate attack, those kind of items. Physical salt attack, freezing and thawing damage, and then special one, reinforcement corrosion, which in many ways is kind of a chemical one. You could really fit it under the chemical, with chlorides moving in there and causing rusting, but it's so prevalent, it always gets it's special and it's talked about by itself, or supplements all these things. And just to further get on those things here, just some quick examples of some common deterioration that you see. This isn't an exhaustive list. I may have mentioned some other ones earlier, but these are the ones that people are certainly familiar with. If you're at all ever done a repair, if you ever walked into like an old parking structure in a de-icing zone, or on a wharf in the sea, you're going to have seen corrosion going on of the steel, causing the surface to pop off. Sulfate attack, often from the wrong type of soil. Alkali aggregate reaction, bad aggregate, the wrong type of aggregate and not being mitigated. Freeze thaw damage, and I like to mention freeze thaw damage because it's not one that typically, I'm not going to say never, but typically leads to structural distress. Very, very rare you're going to have a building fall down or something fall down because it's undergoing freeze thaw, but it definitely will have an aesthetic impact and a usability impact. So all these things, different ways that are motivating your repairs to deterioration, not necessarily structural, your traditional structural kind of concept. And I'm not really going to get into these. That's a story for another day. Hopefully you're all at least a little familiar with some of these things. But I just wanted to mention, these are some of the things that you need to think about when you're thinking about durability and your deterioration mechanisms that you're trying to prevent. And the code really, as I said, you shall consider the deterioration mechanisms, the degradation mechanisms that are happening. So it's incumbent upon the licensed design professional to be familiar enough with durability and deterioration to understand, or at least to be able to identify what's going on and where and what kind of durability aspects may be an issue. Now I'm going to talk a little bit about, and this, the way the code's laid out, and it talks some specific mechanisms that will help you prevent degradation, prevent deterioration. This isn't an exhaustive list, but it covers most of them that are really discussed in the code and different aspects and how they're treated under the code and under this repair scenario. So the first one, kind of the obvious one, and it's the one everyone, it's kind of always been your first line of defense for durability, is really the cover. Cover, super, super important. And really what cover is, if you break it all the way down, is a quality concrete overlay or protection to protect the bars. Protect the bars from attack so that they're not corroded. Protecting bars from fire so that they're not exposed to the fire directly. It's got a little bit of insulation effectively so that they're not. You can get your fire rating, your couple hours of fire rating. Protecting the bar from environmental exposure, preventing the bar from chemical exposure, because fundamentally, concrete super important. I'm not dismissing the value of concrete. This is the American Concrete Institute, but the reinforcement is often the more critical item in the structural performance. So that's, it's save the reinforcement is really the objective here. Concrete, if you lose some concrete from scaling or freeze thaw damage, there's a lot of other concrete there to a great extent, not always, and take everything I'm taking with a grain of salt. Other concrete can kind of share the load, both literally and figuratively, to help out if some concrete is disappearing or having issues. There's a lot less redundancy in the reinforcing steel, so that really needs to be protected. So that's why we kind of want to focus on the cover, think about the cover and how that's going to protect things. And when it comes down to it, there's nothing, the understanding or the ideal behind durability and what their requirements are is that you really must meet the design basis cover. That's kind of the objective here, and that's stated in the code. Hey, we're trying to get the design basis cover. So whatever was the cover that was required by the code that it was constructed under, ideally, that's what you should be getting out of things. Unfortunately, that's not always realistic. Once it's been built, let's say, as you can see in the picture on the right here, it was built and it didn't comply with the design basis cover. The steel was put in the wrong spot, or it shifted during placement, those kind of things, and you end up with basically zero cover in these locations, and that's why you're repairing it. Essentially, you have a structure that, hey, didn't meet the design basis cover, so it's undergone deterioration. We need to fix it. And one option would be just to say, throw up your hand and say, well, it is what it is. This is what we're having. We're going to just get on the cycle of it's not going to be durable. We're going to have to fix it, almost continuously. The history, the lived experience of the structure has shown all these areas that are bad. As part of the repair code, part of the objective to have good quality repairs, we want to do better than that. We don't want to just go oh, look, it was built wrong, poorly from the beginning. These new design people, they don't know what they're doing, but we can't do anything. They just always put the steel in the wrong spot. So we want to get better than that. We want to make sure that we have something that lasts a long time. So the first way to do that, it does say, look, you need to provide in some manner the design basis cover. And the preferred way, and the code kind of tries to push you that way, is if you can add additional cover with an overlay or something like that. And sometimes that's feasible and sometimes that's not. If you're working on a parking deck or a bridge deck and all the cover's really low, if you have the structural capacity, go ahead and put down an overlay, get another inch or two overlay, something that you can do to, when you build it back, hey, we have the cover that we needed, it's going to last and behave the way we wanted to, and we're not going to have a trouble in another 2 or 3 years. Often, though, that's not realistic. You can't put on, oh, let's, it wasn't designed for this, let's throw on another 2-inch overlay. Well, now instead of being not durable, it's falling down because you've overloaded. That's not a better situation. And the repair code acknowledges that. It doesn't want you to put, acknowledges that there will be times where it's not structurally feasible. It also acknowledges that there will be times when it's not aesthetically feasible to add cover. If you're dealing with a facade, for example, that has some areas of low cover that are causing it to crack, you don't want to go, you can't take on the concrete facade and put, another inch of cover over the entire structure. That's not feasible. And you also don't want to go in and put these little block out areas on all the areas of low cover so that when you look at it, it looks like it's got warts all over the structure. We realize that that's not going to be a satisfactory result for the owner, who's the one who's absolutely paying for it. and there needs to be respected. So it does acknowledge in the code that it's an equivalent cover that must be considered. So this is a long way to getting around to saying, if you have an area of low cover, it doesn't say do this, do this, do this, depending on how low the cover, but you are, as a design professional, obligated to figure out a way to give the best solution that you can. And that's often let's add an area of waterproofing or something like that to provide a better cover, a better performance of these steel bars, better protection than you may have had originally, and kind of make up for some of that missing cover. Is that feasible for this situation? Maybe, maybe not, because the cover is essentially zero. But if you were looking for 2 inches cover and you have 1.5 inches, not talking about fire or anything like that, but maybe adding that waterproofing layer is enough to consider it. Look, we have the same level of protection that we're doing, that the original code wanted. So we've made this repair better, and we've considered the situation, and we've done what we feel is a reasonable approach to take care of that. So that's cover. Cracks is the next one, and cracks are obviously a very important thing for durability. Where am I? Yeah. So, but I think the important thing I wanted to start this discussion on cracks is that for repair design, it's different in a many different way than it is for new design structure. New design, there's nothing there, so all the cracks are going to be potentially in the part of the structure that doesn't exist yet, and so you have control over that with detailing and material properties. For repair design, you're only controlling part of it, but it really, the whole structure is what you're considered with. So you need to figure out what's going on the existing cracks, and then what's going to happen, cracks or preferably no cracks actually in the repairs. The nice thing about considering the cracks in the repairs, there's a lot of information out there from new design structures that people are familiar with. You get the right detailing and you get the right situation, and you can avoid those type of cracks. But the code does ask you to think about that. How are we going to avoid these type of cracking? Getting the right material properties, getting the right compatibility. If I could call back to what I talked about earlier, the right bond, lower shrinkage, those kind of things. That's definitely does need to be considered. But also the existing cracks can't be ignored. Some of them will go away when you do your repairs. So you're looking at a big spall and you've got a crack in your spall. You don't need to worry about that, because the first thing you're going to be doing is demoing out that spall and all the cracks that are associated with it. But you really need to evaluate the impact of the cracks that will likely remain. Is this something that we can deal with that will not have an impact? Or if it is going to have an impact, what do we kind of do? So when you're thinking about these type of cracks, I'm going to talk mostly about, in this section, the cracks that remain, because you should all be familiar with avoiding cracks in the new portion of it. You really need to start thinking about why you have a crack and what is it doing. You need to think about what caused it. Is it going to move? Is it size, orientation, its width? What are the characteristics of the crack? You must understand that, and the code needs you to consider that, so you can understand its impact, so you can figure out the right way to deal with it and what is the right approach. Is it a structural crack? Is it a non-structural crack? Is loading causing it? Is it due to some other deformation? Is it due to volume change that's kind of done at this point in this old structure? All these things go into it, and to allow you to evaluate what is going to be the impact on the performance of the structure, and not just its structural performance, but equally its durability or its service life performance. And also what's the best way to address it. Like if it's really a narrow crack, really a thin crack, maybe you don't need to do anything. It's not really letting in much water and it's not having an impact. Or But if it's water, maybe we do need to inject it, or maybe we do need to provide a coating to keep everything out. If we just have one crack, maybe that's a good candidate for injection, where if you have 1,000 cracks, maybe that's, you need to consider it, whether it needs to be coated. So the way the code works about this is, again, it's more about you shall consider these effects. It's not specifying specific amounts. Like, it doesn't say cracks over this width shall be injected. It's onto the licensed design professional to understanding for this situation, for this aspect, how that's going to behave in the structure itself, and what impact that's going to have. And then, active or dormant cracks. Is it moving? Is it not moving? These will have an impact on how they're addressed and what approach they're going to be done to, resolve their impact. And even if they need to be addressed at all. If it's an active crack that's moving, you need to be able to make sure that you're doing a repair that doesn't lead to it cracking again. Those type of things need to be considered when you're doing your durability repair design. So just to kind of sum her up, the design of your repairs for your cracks needs to consider the effects of your cracks on your expected durability, its expected performance, what the expectation is for the structure as well. If you're repairing something that, we need you to repair it, we need to limp it along a little bit, but 5 years we're going to be demoing it and building up the latest and greatest, that may be a different repair approach than to one like, hey, I have the structure, I'm going to be owning it for the next 50 years. You need to, try to get me as close as you can to that level as well. And again, it's also different than in a new design structure, where you need to think about not just the repair, but the structure as a whole. What is the repair doing to the structure? What is the structure doing to the repair? And what's the condition of the structure away from the repairs, and how this cracking will affect all of these aspects, and figuring out the appropriate approach for those situations. Just wanted to touch again, while I'm talking about crack, there is a lot of different repair materials and approaches. One of the most frequent is epoxy injection. And if you're not familiar with the ACI wrap documents, they're an excellent resource for information about repairs and repair approaches. It's in many ways written to the contractor viewpoint, but as an engineer, I find it invaluable, understanding what are the limitations, what are the requirements of the repairs. So they're very short documents, they're very practical. If you're not familiar with them, definitely seek them out. But again, crack injection is obviously an important way to address cracks, and you can look at both epoxies, which are rigid and provide structural performance if that's what's necessary. But if it's not necessary, there are some more flexible approaches or things that can be injected, such as your polyurethanes. It's also, when you're evaluating repairs and evaluating the cracks, you should also be thinking about maybe the best way, if you have a lot of them, is looking at a coating system or something like that. So there's just, cracks, it's, in some ways, hey, just inject all the cracks, it's easy, go away onto the next one. But it does have a significant input, and there's, depending upon the characteristics, it is something that you should think about. What is the correct approach for this, the most appropriate approach for this situation, and not just, oh, I did this on the last project, it worked then, I'm going to do it on this project and not think about it. So it is an important aspect of things to think about. Next one, wanted to hit on, that's kind of, we've covered cracks and preventing deterioration or degradation. Corrosion, the kind of special little system that is just so important that it requires its own description, in addition to all the other degradation mechanisms that can happen. So corrosion, everyone, hopefully you're all familiar with it. It's rusting of the bars, the rust expands, it'll pop off the steel, you get a spall. That's fundamentally the corrosion process. It's due to chlorides, it's due to carbonation, not really going to go into here. That's not the objective of this service or this presentation. However, what the code does talk about that I do want to highlight right first is that you need to consider what the corrosion has done and how it's will affect your design service life as well as other performance requirements. So it doesn't mandate that you need to remove all the corrosion product from the steel, though there's a strong bias towards it, but it realizes that there may be situations where it is not technically or physically feasible to remove all the corrosion. You know, it is trying to be a practical document that people can use, and doesn't not put you in boxes that you can't get out of, but it does want you to consider what the corrosion, you know, if you can't remove the corrosion product on your steel for whatever reason, it will have an impact on your design service life. You need to evaluate that and try to overcome it in another way. So that's kind of the first, and I think that in some ways that's the most surprising to people about the corrosion portion of the repair code. It's kind of like, well, of course we want to move corrosion products. Why wouldn't you? And I think the committee, we would agree, but we also realize is that, hey, there are a few very unusual situations where it's not going to be feasible, like you can't access it or something like that. But you also need to consider, and you know, this in some ways is less of a durability issue, but it is something important want to raise, is that you're not just considering the effect of corrosion from a service life viewpoint, but yeah, structure is still important. So if you lose too much of the section, which really should be determined by the structural, what the maximum amount of loss is, you know, 10% or 15% frequently thrown around as a guideline number, but that's up to the structural engineer. You're going to need to address this loss of section over this effective length and restore it to the structural performance. And the easiest way to do that is then lap in a new supplemental bar. Easy conceptually, most of the time it's fine. Some of the bigger bars, however, it can be a little bit challenging because these required lap lengths, which need to be done by 318, can be very, very long. And there are situations where, you know, you've done the demo, you've exposed all of the corroded steel, but it's particularly if you're losing a lot towards one side of your opening, the lap, to put in the required lap, may need to extend into, you know, require additional concrete removal, extend into the otherwise good areas. So sitting here today, I don't have a good solution for that, because you need to remember it's not just, you don't just need to lap the new bar, but you need to have that same lap on the effective length. So, you know, an epoxy anchoring it isn't necessarily the right solution. But really the idea, you know, what I always try to do is, even if you have a big bar that's lost a significant portion of it, you may not need to supplement it with the same size bar depending upon the amount that's lost. You can use, and that will allow you to use a shorter lap length because it's a smaller bar you're putting in, at least to a certain extent. But that is really something that the structural engineer, kind of that decision needs to be made by them and evaluate that on a specific basis. But it is something to think about, and because it may require you, if you're not careful, to remove a whole bunch more steel than you would, or sorry, a whole bunch more concrete than you otherwise would. And again, you know, I think everyone's familiar with that, but just quickly throw in this. You know, really what we're doing, the repair mostly we're talking about is, and I'm going to talk about mostly going forward explicitly, are these partial depth patch repairs where you're removing, you're replacing your contaminated concrete. That doesn't mean that the same aspects don't apply to other situations. but this is just the one that is frequently more comes up and is what most people think about, and is a good example of how you need to think about these things from a durability perspective. It can be an effective solution, but you need to do it the right way for it to behave properly. And the reason for that is really what I'm going to describe now. That the reason, that it needs to be done correctly is this concept that I'm going to be presenting right now, and that's really what you go into it, and you do this localized repair, and you create this passivating layer over the steel that's in your repair. So you clean that steel, it's not rusted anymore. You don't need to lap anything in because you haven't lost a lot of section. Hey, you put the new repair material in, it's new concrete. Steel and new concrete doesn't rust. Hey, you're really good. Well, you are in the localized repair area, but it's only protecting the stuff in the repair. And while you may not have had corrosion outside of the repair, you may have got all the steel that was corroding, there's still a level of contamination in that original structure, in that original concrete that's still hanging around. It may not, may have been protected by the steel that was corroding, but now that you've stopped that, you no longer have that protection. And if you don't know anything about corrosion, what's causing corrosion, the easiest way to think about it is corrosion is driven by differences. You have a difference in temperature that can cause corrosion. You have a difference in water, moisture content that can lead to corrosion. You have a difference in chloride content that leads to corrosion. So what have we done? We now have a portion where we've repaired it that is not contaminated at all, but immediately adjacent to it, we do have a portion of concrete that does have some level of chloride or some level of carbonation. This is more important from a chloride viewpoint, but and that will then kick that off and accelerate corrosion around the repair. And this is called the ring iron effect. But really what it's saying is it's not unknown or not, it's fairly frequent. You do a set of repairs, everything's beautiful, you fixed all the areas that are bad, you come back 3 to 5 years later, all your repairs are doing fine, but you have a whole set of new patches immediately adjacent to them that you have to address. This is why that's happening, the ring anode effect. Well, how do we avoid that? You can't avoid, the right solution isn't, okay, we're going to prevent the difference, we're going to add chlorides into the localized repair and then match everything so nothing's the same, but then you've got a lot of salt going. You really need to think about electrochemical solutions. And there's really two types: electrochemical cathodic protection solution, your galvanic anodes, and your impressed current. And the way these work is really by adding energy into the steel. The way we get steel, we dig iron ore out of the ground. That's essentially a whole big chunk of rust. It's iron oxides. We then add a bunch of energy into it to drive off all the oxygen and all the water and all the stuff that's making it rust, and we come out with nice brand spanking new iron or spanking new steel, which is iron plus carbon. But nature doesn't like that. It wants the iron to go to rust. So we've put all this energy into it in the furnace. You put it back out in nature, and nature wants to drive it back to the rust. Well, the way we avoid that is we add energy from this cathodic protection system, and we keep that rust going back to iron. So, it's not. I'm saying here rust iron. It's not really enough to do that, but that this is from a concept. But the reality is, we want to keep the iron or the steel as iron, and that's what the energy is doing. You're adding this energy to overcome your nature's desire to get it down to rust. As I said, there's kind of two main categories, what's often referred to as galvanic cathodic protection system, compressed current cathodic protection system. This isn't a course on CP. People could do hours on this. I'm just going to hit the highlights of the differences so you can appreciate what's going on. Galvanic is what's referred to as a passive system, which is really coming from there's no internal power supply. So there's nothing that people have to continuously actively do to get the galvanic system to work. Whereas an compressed current cathodic protection is an active system, and you need to supply external power, coming from your power plant, coming through the wires and getting into your system that provides that protection. But because the galvanic cathodic protection, it's not, from a power supply, what's happening is it's provided by different position on the galvanic series. So, you've seen that all in school. You've got, different metals in a list. When you connect them together, one of them rusts and one of them doesn't. We're taking advantage of that property, that galvanic series, and using that to make sure we protect the parts we want to protect. And really the reason, conceptually or simplistically, that the galvanic series is providing protection is because you're supplying energy from one to the other. So, but to do that, if you have a passive system, you're going to consume the anodic material. So if you have zinc in there, it only has a finite lifetime because the material is consumed. Whereas because of the compressed current, you're provided by adding energy to the system. The anode material in general is not consumed. You're getting that stuff from outside. In theory, your compressed current system could have a much longer life than the galvanic cathodic protection system. Not always true in reality. You get other things that control its life, like the life of your rectifier, et cetera, just plain old damage to it. Someone bumps your wires, but theoretically, you design your galvanic system for a certain lifetime, whereas your compressed current cathodic protection system, can go for a lot longer if everything behaves the way it should. Simplistic, there's a lot more details that go into CP, but that's, kind of the 2-cent version of it. Did want to touch base, kind of let everyone know there are a lot of different form factors that cathodic protection can be used, and some of them are more appropriate for different types of repairs. The one that is most commonly used, particularly for the ring anode effect I just described, is more of a point anode system, where you have discrete anodes placed around the patch, or in the structure, and they're typically a galvanic system, though there's no reason they have to be in theory. There are manufacturers who do have ones that have a battery in there providing that external energy, so they are an compressed current system. Frequently they're a dual system, but again, I'm getting off topic. That's kind of one form factor that you can put into, that you can do with, you can develop a cathodic protection system or incorporate it into your repair. Embedded in mesh anodes is another way to do it. Again, in reality, in theory, there's no reason this could not be an compressed current system or a galvanic system. But however, they're more frequently used as a galvanic system, where your mesh is consumed as it goes. It just seems to be an easier way to deal with it. Whereas surface-mounted anodes, where you have a metallic coating, that they tend to be more frequently used with an compressed current system. Though theoretically, they could be a galvanic system as well if you do a zinc spray on it. That actually, that happens. That's another way that you can see it. These are kind of, you have both as an option. And then jacketing systems are another way. Frequently used for an compressed current system, also can be used for a galvanic system, and this is something that's frequently used in marine environments, where you have your pier, you put in a form, you put a cement a concrete cement cementitious kind of jacket around it and embed your anode in there. That can either be the inert anode for an impressed current system or a sacrificial system. Sometimes you even get really fancy and you use FRP for formwork as well. So again, cathodic protection systems, it's a good way to overcome some of the problems you're getting into when you're doing these partial duct repairs. And depending upon the specific project and specific aspect, you can really do this in a variety of ways. Wanted to kind of just delve down a little bit into two of these systems. Point anode systems. These are the hockey pucks. They're the ones that are most frequently involved in the partial duct repairs. These are ones that a lot of the manufacturers supply enough information that someone who is relatively uneducated in terms of cathodic protection, it's not a specialist, they can provide that, they can incorporate in their repair program successfully, very simply. They may need to be making decisions in terms of spacing and things like that, but really these can be incorporated in your patches by most structural engineers if they so desire. Just that they have enough information from the manufacturer. What's the spacing? Where do they need to put them around the shape of the repair system? Whereas contrast that against an impressed current system, and they need to be very specifically designed for that structure. There's a lot of decisions that need to be made in terms of what the anode type is. So what that, are you using a titanium anode? There's different options there. What's the power supply? How much power you need to produce, need to supply, and then zoning it. And there's all sorts of decisions. And these type of systems are most frequently designed by a specialist. They often can be done, that can be done by this engineer of record, or this is frequently incorporated using, as a design build, a delegated design approach. But it is something that can be very effective in a repair, kind of overcoming some of the corrosion issues that may arise. One last, it's a couple little bit things, and I'm kind of coming up to the hour. Surface treatment is something that's considered in durability. The big aspect of it is it does allow you to consider surface treatment in terms of your protection. It's not something like, well, we don't care what your surface, if you have any coatings or membranes or sealers, you still need to be durable beyond that. It is something that can be considered, and the selection of the material of the right system depends upon what the specific situation and the exposure, the orientation, wear, and aesthetics. I'm quickly going to touch on the three common types of coatings and membranes. First one is a sealer, kind of the original one, or in some ways the most basic is one of the words I use, but it can be very effective. And that's just a clear liquid that's sprayed on, absorbed into the surface layer, and it repels water as it lines the pore. But the nice thing about it is at the end of the day, you can't tell that you have it visually. It does retard the chloride from entering, but unfortunately, because of the size of the molecule, it doesn't really do much help for carbon dioxide. And the important thing about all these coatings, once everything that's in there, it's not magically disappearing them. They're still there. You need to take that into consideration when you're talking about durability and life. Membranes are another one, or really coatings, very physical barrier. This is kind of it's a type that has a lot of different ways, form factors, a way of doing it. Showing like a polyurethane membrane system that's squeegeed over the surface. But in this category, if you're dealing with a facade, would be stuff like coatings as well. And because there's something that's applied to the surface, one of the aspects of it, it does have an aesthetic impact. So you need to consider that, make sure that the owner is expecting all of a sudden you have a gray a gray surface, a gray rubber surface, instead of your nice shiny new concrete. As you know, you need to prepare them for that. But the nice thing about membranes is what they're really doing is they prevent anything from getting in, water from getting in. So it'll prevent chlorides and carbon dioxide from entering into your system. And the nice thing is, even though it doesn't address the existing contaminants, they're still there. It can, given time, reduce the moisture that's in your existing concrete, and that can lead to reduced corrosion rates. Some people think about that's more important than others do, but it is a potential, depending upon the situation and given the time, that it is an additional advantage that, hey, well, we're not removing the contaminants, we're removing the water that allows the corrosion to go forward, or at least reducing it, trying to slow it. And then the third coating wanted to talk about, and coating may be a little controversial, I just put it in this category, is migrating corrosion inhibitors. I do want to put a big caveat on this. This is something that, to a certain extent, is a controversial, unproven technology. Some people think it works better than others, but the idea is you spray on the surface a corrosion inhibitor that works its way down to the steel, and then, similar to a corrosion inhibitor that can be added to the concrete at construction or an initial construction, it then provides a certain level of protection. Some corrosion inhibitors work, migrating corrosion inhibitors work. I've seen data that shows that they work. I've seen data that shows that they don't work. Again, some of it depends upon the situation. If you have steel that's relatively shallow, it's maybe a lot easier for the corrosion inhibitor to get in than you have steel that's very deep. So this is something that I think it is good for the licensed design professional to be aware that exists, but prior to doing it, they need to evaluate whether it's the right solution for their job and for their specific project. And frequently what we're seeing nowadays, which is kind of more justifying why it's in the coating, is it's combined with a sealer, so you kind of got two types and two levels of protection, more of a belt and center space. So kind of watch this space. This is something that you should be aware of. May be right for your situation, but not necessarily meets all. Not necessarily something that can be used every case. Chapter 8, durability. One last aspect I want to really quickly hit on is the maintenance program. Maintenance is an important part of durability. If you remember back at the beginning, I talked about durability has a time aspect to it. Maintenance is an important part of that, and this is a quick definition of maintenance, but more very formal. But it's really the idea is it's what someone does to keep the structure behaving well. Repairs are part of maintenance, but maintenance is much more than repairs. Excuse me. There's a lot of different things that go into maintenance, and it varies from your day-to-day, or you're sweeping it down, something that can be done on an annual basis, like washes, or to more intense activities during a shutdown. It includes all of that. I'm sorry. And then the big issue is that from a code perspective, it doesn't require the licensed design professional to be responsible for the maintenance, but they are responsible for understanding and communicating to the owner what level of maintenance is to be expected to achieve the durability. So chicken and the egg, I don't know where that's going to, but that's something that should be considered. Really just briefly touch on this. Most people have probably seen this. De Sitter's Law of Fives. Summarizing this down into one sentence, the earlier you do something, the better it helps. If you can get in before things are really bad, you're getting a lot more bang for the buck. Don't know where 5 comes from, more conceptual than actual, but the idea is you get, the more earlier you get in there and do something, the much better it happens, better results you get, and it can really exponentially take off. Covered a whole bunch of stuff on durability. ACI, does have a lot of references. I'm not going to go over them. These are more here, so they're in your handouts. But there's something that you can go to, and really, if you want to dig into, they need to dig into a topic, they're a good source for you. Now I'm going to move on from the durability chapter, which is obviously something I think very important, and get into the final 2 chapters of the code. These are a lot shorter, don't worry. I'm not going to drone on about these as much, but there are some important aspects we need to talk about. First one is chapter 9, construction, and you can see that it's the second last one in our little path through the code. But before I really get into what's actually in the construction chapter of the code, I want to emphasize what its objective is. Just like the construction chapter of 318, the intention isn't to provide direction to the contractor, but it is to provide direction to the licensed design professional to provide information and directions to the contractor. So what construction related aspects does the contractor need? Does the contractor need information from the structural engineer? Because in the ACI world, and really the way it should be done, codes are directions to the engineer. There are other documents that are required that are provide directions to the contractor. So if you're familiar with 318, 318 is the directions to the engineer, the licensed design professional, but there's a companion document, 301, that provides directions to the contractor. Similarly, for 562, there's a companion document, 563, that gives you direction, that gives directions to the contractor. And what 563 are a set of specifications for repair programs. A guide or specifications, very similar to the 301. Some of it is very similar. If you look at, this is the table of contents, it talks about conventional concrete mixtures, handling and placing, but it also talks about things that are very specific to repair, concrete removal, chapter 3, or proprietary materials, so your bag materials, chapter 8. And one of the things it also does is it acknowledges that, hey, there are things that are very much necessary as part of a repair program, but guide specifications or specifications are already developed elsewhere in the institute, so it just provides a reference to those rather than trying to reinvent the wheel. But these are, if you're in the repair industry, these are something that are very useful to be familiar with, either to use on your projects or to use to develop your own specifications and see what's important. Again, very, very similar in many ways to 318. Contractor is still responsible for means and methods and job site safety. That does not change. They're responsible for complying with the construction documents, providing access for QC and inspection, and are responsible for designing temporary shoring and bracing. But there are some aspects that the licensed design professional needs to provide, some limitations that they need to provide so that the contractor knows what they can and cannot do from a safety viewpoint or from an structural viewpoint or what have you. And one of the critical ones that becomes very important in repair is providing limits to what concrete removal. And the licensed design professional, because they're the person that is responsible, is not familiar with the performance of the structure from a structural viewpoint, and if they have done the assessment, they're the ones that need to provide these limits. Now, if you look at the picture on the right, this is a column that a lot of the concrete has been removed, and every time I look at that, I get a little bit scared because I can see that that bar on the right, it's no longer, it's engaged by the ties, but on the inside, it's not being held in position by the concrete. So there's a potential that that bar, since it's still under load, could buckle inwards and cause that concrete to fail. So the licensed design professional needs to provide limits to the contractor to the extent of how much concrete can you remove, what you need to do in these type of situations if they encounter them, providing these requirements and providing these limits. A similar situation, pre-stressed concrete beams. If the beams are under stress, there's only so much concrete that can be removed, or else bad things will happen. You could lose your anchorage, or you could cause the beam to deflect excessively, or crack, or fail. These types of information, the person who is most familiar with the structure is the licensed design professional, and needs to provide guidance to the contractor what they can and cannot do. This isn't determining their means and methods. It's not saying how they remove it or how they do that, but just providing a limit so that they understand what they have to do in the box that they're playing in, kind of thing. So that's the construction chapter of 562 provides direction that way. It also focuses, bracing and shoring, important thing, very important in new design as well. But the difference is, in new design, the structural engineer is familiar, the designer is familiar with it in the final condition, but they're not aware of what's going on at different stages. That's under the means and methods of the contractor. Still the case in terms of means and methods and different stages during construction, but there's an important aspect on that the licensed design professional has performed the assessment and is familiar with the existing conditions, and and that may limit what the contractor can do. So these limitations, need to be communicated to the contractor, and particularly if they need to be aware of these things, particularly if they're walking into a situation where some temporary shoring has been installed, and they need, the contractor needs to understand, okay, I now in control of this job site, but I have the shoring that, I wasn't responsible or I wasn't designed for. They need to know the aspects of it need to be communicated to them so they can understand how to deal with it and how that will impact the construction process. But other than that, you need to consider, all the same things for shoring: global stability, lateral forces, what you're doing to the load path, all those things that are typical for a shoring project. Temporary conditions, it does 562 does reference or acknowledge that ASC 7 and ASC 37, the design loads for structures during construction, are present. It is, a useful document, but it does begin to be a little bit tricky, and it's something that the licensed design professional needs to consider and needs to communicate when only a portion of the structure is being shut off while the other portion of the structure may be open to the public. What are the appropriate loads when it's not construction? You're dealing with a structure that has partial construction loads and partial not normal loads. What are the appropriate load factors and loads during that situation? So it does get a little bit trickier in many ways during a repair project. Environmental issues are also something that's addressed in Chapter 9. What's the and that's it really breaks it up and sort of into 3 different types of environmental issues. And the first one is things that the licensed design professional is aware of at the start of the project. In that case, they're responsible for informing the contractor that's what's there, and informing and including mediation requirements, either as part of the contract or prior to the contract, so that these environmental issues are addressed. The second thing that acknowledges are types of environmental issue that the licensed professional needs to consider and communicate this responsibility to the contractor is if there are unknown conditions or new conditions that are present in the structure, but the licensed design professional after a reasonable due diligence, was not aware of them. So what is the responsibility of the contractor in that case? That needs to be communicated as part of the construction documents. And it's typically things like, they're not allowed, they need to not disturb it and report it to the licensed design professional and to the owner, and then the owner, and then that how to mediate it and who's responsible for mediating it can then be decided at that time. It is the owner, it'll be the owner's financial responsibility, but what the decision needs to be taken. Well, should the contractor do it? Should we get another mediation contractor? And what impact will that have? But 562 requires the licensed design professional to require the contractor to communicate to them if they encounter any new environmental conditions that need to be addressed. And then the third aspect of environmental conditions are things that are not a part of the structure, but part of the construction process that are generated by the contractor. And in that case, the realization is they're the ones who are controlling of it, so they're the ones who are responsible for mitigating it. And these are such things as, good example of that would be like dust. If you're doing a lot of demo, you're going to get a lot of dust. It has to be made clear that the contractor is responsible and what type of performance or what are the expectations to control that construction, that environmental issue that's developed as a part of the construction process. So some of these are not really new, but it's certainly acknowledged in the code and is a way to move forward. I'm going to briefly touch on a couple of different repair processes, how to get, really how to get the concrete into the hole. And again, I want to refer you to these RAP documents, very, very useful. There's a lot of them. I'm going to try to focus on 4 of them that really are different ways you can get, the concrete into the partial depth repair that, the hole that you've created with your, your chipping hammers. First one, very similar. It's the one that's kind of most similar to new design, to new construction. You're basically getting your concrete from wherever your supplier and pouring it in and vibrating it and finishing it and all that kind of thing. Similar type of formwork may be necessary, though sometimes formwork isn't needed if your partial depth repair will contain the entire concrete. Similar type of curing, similar type of stuff, but something that's should be very familiar to anyone that's been on a concrete construction project. It is in many ways not very conceptually different than new design. Form and pump, a little bit different in that instead of just pouring it in and working its way under gravity and then with some vibration, the new repair material is injected or put into the cavity under pressure. And the advantage of this is it kind of helps get the repair material into intimate contact with the existing concrete, so it works on the bond, and it helps it get into places it wouldn't otherwise go. So you often see these type of situations in when you have a congested area, a congested structure, lots of steel going on. Biggest difference, the pumping equipment. You need a lot more higher pressure than your normal pump. It's not a normal concrete pump. And then also the formwork needs to be designed for the pressures. So you often see the formwork, as you can see here, a lot more stouter than you would normally get it. Given the size of this, that's some pretty stout formwork we have here. Not really a lot to say about hand patching. It's kind of what it sounds like. You make your mortar into something that's sticky and you kind of put it in place and finish it off. It's kind of not as commonly used as some of the other ones, but what it's really effective for is very small areas. But otherwise, if you're trying to do a large area, it can be fairly labor intensive, and you often run into issues with it debonding because you're relying on the worker, the mechanic, to force it into place underhand. There are specialty mortars that are designed to be used in this situation that have bond enhancers, but really only good for when you're really dealing with a small area, such as what way this picture is shown. Shotcrete, however, Not something you encounter in new design, though it is, it was developed and started in the mining and tunneling industry, but it's found to be very useful from repair concept, in the repair field. Kind of two aspects, two different methods of shotcreting. The wet process and the dry process. Wet process, you get your concrete, it's already mixed together. The water and the dry materials, you get it from like a ready mix truck. Goes through your pump with an air compressor, and then the nozzleman, sprays it into position. That's the whole, that's the shot part of the shotcrete process. Is where shot comes from. One of the biggest drawbacks from that is you can get some rebound, whereas you're spraying it against the surface, all these stone and sand and things, some of it will bounce off and you end up with a big pile of stuff at the base of your repair area. This is really good when you're doing large areas, because then you can get the ready mix truck and everything's wet and you can kind of just go and go and go, and it's a lot more convenient that way. Dry process, frequently used, a lot more convenient when you're doing small areas or a bunch of small areas. The difference is the two is you just mix your pre-bag material. You may, essentially it's going through your gun dry until right at the end where you're adding the water. The nozzleman adds the water as kind of they go. One of the challenges of this is that you're relying on your nozzleman to control the amount of water in your shotcrete. So it does rely on an experienced nozzleman to get it to be the right consistency. So it will, it's not so dry that it's not going to, it's not really concrete, it's just a bunch of powder, but it's not so wet that it kind of sags and sits and has all these, doesn't have the properties you kind of need. Generally, for the way I do it, shotcrete I think is a very good process, but I let the contractor figure out which is the right one for them, for the way they do things for that situation. Even though, as I said, wet process is for big areas, dry process for small areas. It's more important the contractor is comfortable with what they're doing, and I don't like, as an engineer, controlling them the way they're doing stuff, what's more comfortable for them. You end up with the same product at the end of the day if everything's done right, and you still get rebound with both situations. There are some advantages. It can be very economical. You don't need to build a whole bunch of formwork. Because you're forcing things into it, you don't need a bonding agent, and you kind of end up with something that, hey, you got the concrete where you need to go. Disadvantages, you do need to deal with the rebound, and you do need to, make sure you're not getting any voids, you're not missing any areas. It really depends upon having an experienced operator at the end of the nozzle, the one who's applying it, making sure you end up with a good situation. These are some of the things that you need to consider when you're thinking about rebar, whether shotcrete's appropriate, how you're going to be building up some of your thicker sections. You may need to do it in multiple layers. It can be time consuming for large areas. It's not, you're not, volume you're applying at once is limited to the size of your hose. You can't dump a big pile of concrete the same way when you're forming and pouring something like that. Control of rebound comes into a thing, and then but it does still need to be finished. I mean, I have done situations where I'm repairing something that no one really thinks about, so you don't need to finish it, but most at the end of the day, finishing isn't important, so you get a very similar surface texture. Just basically, the only thing I wanted to mention on this one, you kind of, you need to do a good job, fill everything. The tricky part is, since you're spraying it on and it doesn't flow anywhere, getting behind the bars can be tricky. You can kind of do it from an angle, and they should, but it's helpful if there's the opportunity to use a non-contact lap splice instead of a lap splice. It's just, you don't have this big area you're trying to get behind. Again, ready mix, wet mix, site batched, prepackaged. There's a lot of different sources for your shotcrete, and some of the material properties like shotcrete is a lot more convenient to use fibers since the concrete doesn't have to flow. You don't get some of those issues that you can get with fibers. Using supplementary sedimenting materials, perfectly possible with a shotcrete system. And actually some of them, like silica fume, I believe, generally tends to help the rebound. There's other additives that can be done. It's a concrete mix just like any others. You can do a lot of, better living through modern chemistry. A lot of the admixtures can still be used. And again, similar, this is something you need to check it. All repairs need to be done the case. You need to make sure that it's done correctly. So that's like the construction chapter. Moving on to the next and final chapter, quality assurance. And as I said, it's the final one in that, in this long path that's been taken through ACI 562, kind of coming to, QA and QC, kind of the last aspect that needs to be considered as part of your design. Quality assurance, important for new structures, equally important, if not more important in some ways in the repair industry. But conceptually, it's something we haven't reinvented the wheel here in 562, kind of the same aspect that going in, you need to review the QA program, establish effective QC stuff, review your conditions and test the materials, all that same conceptually idea. The chapter 10 in 562, it puts this is directions to the engineer, and it's telling you that these requirements need to be placed in the construction documents, and they must be specific to the project. So this is not the place to go, oh, this is what I used on the last project, I'm just going to shove it into this one and hope everything's good. If you want a good project at the end of the day, QC is something that you need to think about and figure out how that should be applied to the specific project. With that, I'm kind of going to try to focus on some of the things that are specific to repair programs. First one, this also is true for new design, but I find that there is much more likely to be a lot of special inspectors for new design. In my opinion, to the greatest extent possible, the licensed design professional should inspect, their projects. They're the ones who are most familiar with the assessment and the idea of what's going on and what the intention is. They should be given the opportunity to see the final product or at our intermediate steps, so to understand that it meets the requirements of the construction documents. However, it is realized that that's not always going to be the case. And ACI 562 does allow the use of, repair inspectors or a combination of repair inspectors and design professionals. So a third-party repair inspector can also be involved in inspecting and ensuring the quality of the repair work. Although, in my opinion, licensed design professionals should always be involved. Repair inspector, should not be just some Joe off the street. No offense to Joes. It's someone who has a certain amount of qualification and experience. And some of this is outlined, the jurisdictional authority may have an opinion on what's an appropriate repair inspector, but there are certification programs. I know ICRI does have an extensive program that, qualifies someone to be a repair inspector. And that should be implemented, made very clear as part of the project, either construction documents or the discussions with the owner, that this needs to be done, and it needs to be, the right person. It's not just your maintenance guy going out and having a look at it. Just some of the ideas that testing and inspection may include, nothing earth-shattering here. You're looking for the quality and that it meets the design intent. So, quality of the repair material, the right formwork, whether the concrete removal is done correctly, whether you end up with a surface prep that you need, if everything's replaced, your formwork and your anchors and your reinforcement are in the right place. normal things that come as part of an inspection program. Again, often though, it's not just, okay, was it built correctly, but particularly in the repairs, you often encounter things that are not what you anticipated. No matter how much assessment you did at the beginning, you may, you come up with things that are different at the end. And part of the quality assurance process is documenting these differences so that they can be communicated to the owner, whether they have an impact on the repair that's being done, or the quantities, or the locations. These things that need to be documented, and the licensed design professional needs to weigh in on making sure that these are appropriate, but also that this is communicated to the owner if they have some sort of different impact on the cost and things like that. So not strictly quality insurance, but that is also something that comes into it. And really, at the end of the day, we want to end up something that, ideally looks, at some of these, those photos or that little diagram at the end, everything's nice and square and round. Square for the cuts, round for the bars, everything's clean, the right roughness, and now you end up with a good quality repair and a good quality replacement concrete. Again, basic stuff, but it does, the licensed design professional, they need to communicate that the existing conditions not be concealed prior to inspection. That opportunity needs to be given just as part of the quality program. And but one of the most unique things, and this may have been touched on earlier, for a repair project as part of the quality, is really the effect of bond. Bond becomes very important, as I kind of alluded to earlier, and I'm sure was discussed equally in the structural portions of this webinar series. And depending upon the stress at the bond, different types of quality assurance may be necessary, different types of testing. And for lower areas, the stress is relatively low and it has a very specific guidance what bond integrity testing can be performed. And bond integrity testing is a very fancy word, but really what that comes down to is if you're doing a bunch of repairs and they're relying on bond to the concrete, and that they need to be at the very least sounded so that they aren't falling off, even before the project's done. So the idea is you give them a little bit of age, you let them shrink so that the stresses develop at the bond, and then you can go out and sound them, and hopefully everything's still in place. And if they're not, they need to be redone. Sounding is kind of the most common way and most simple way, but you can also use non-destructive techniques if that's appropriate, such as ground penetrating radar, impact echo, ultrasonic pulse velocity, some of those fancy things. Pull-off testing is useful or is required by the code at a higher level of stress, between 30 and 60 psi is the way it's written right now. And it does mandate, the frequency of that testing is all mandated in the code. This needs to be communicated to the contractor. But again, this is something that, very specific to a repair project. If you're relying on the concrete bond, and it's very important from a strength viewpoint, there's a little bit more, and you're not, you need to really reassure everyone that this can be developed through pull-off testing. And, but if it gets, the code does limit, and I'm sure this was discussed before, a limit to the amount of stress that can be across, that can be communicated just by concrete. It's not permitted to have these higher levels of stress because you need to implant, you need to use some steel anchors or something like that. So that's something that's an important quality assurance that is kind of unique to repair. So I definitely wanted to mention it. Another one that is kind of very common for repair, that can happen in a repair. It is, not something that does not occur in new structures, but it's frequently much more important and much more frequent in the repair industry are post-install anchors, so your epoxy anchors. And they're needed for a variety of reasons in repairs. Often you're just running out of space and you need to, develop and anchor your bars, one very common one. These should be inspected by a certified, anchor inspector, and ACI does have a program that you really should be requiring the person who's inspecting the anchor installation to have been through, so that they know what to look for and what is a correct anchor installation, so they are familiar with it. So those are two kind of aspects from the inspection viewpoint that are not unique to repair, but are can be very important in the repair industry. So you should keep those in mind. And commonly, this isn't something any new. If you have non-compliance, you need to come up with a corrective action. This is something, that's pretty straightforward and pretty option. Not, if things are different, they're not doing it right, they need to come something with a corrective action. Sometimes it's things that are not out of control. They're not in control of the contractor, so it's not always something that the contractor is responsible for, but they should be responsible, with the appropriate compensation for developing the right corrective action, for implementing the right corrective action. So they're the ones who are on site. If there's more quantities, or if there's something that they wasn't anticipating, the contractor, it should be made clear that the contractor, with the appropriate adjustment to the contract, does it and addresses it, but it's not something that they can just walk away from. Quality assurance, the final one, it does describe or talk about testing of repair materials. And many, some of the testing requirements may be a little bit different than what you would get in new structure, but cylinders are kind of the same way. Sometimes you're more going to have cubes for mortars, or you may need to do, if your shrinkage is important, the ring test rather than the linear shrinkage test. But conceptually, it's the same. No matter what type of project it is, they need to maintain the testing records. So that's kind of, I've gone through the code, or the last part of the code. That's the final chapter. Kind of in the next few minutes, I'm going to very quickly go over an example, very detailed example. Where this example came from, this guide document, ACI Manual 3. It's available. It goes through this, not just this example, but a number of examples in detail, so you can follow what the process was to comply with the code, as well as the process, as well as not just, oh, this was a good repair, but how it was accommodated, how the code requirements were accommodated, and how that process kind of went through. I'm going to warn you, I'm going to go through this very quickly. I'm not going to get in, there are a lot of calculations and things I'm not going to get into, but hopefully if you have the handouts, you can take your time at a later date and work your way through the calculations, or again, get this manual that has a lot of numbers, has a lot of these different examples laid out already. So what this situation is, it's a water treatment plant, and essentially what's happening, the roof was constructed of precast double T roof beams with dents. Cast in place concrete framing, so not an unusual building type. Here's just the plan, get an idea, this is what the roof looked like. Remember, this is the roof, so the pump room is below, the steel tank room is below, but you really just have a number of double T's of various depths, various lengths, et cetera, et cetera. And this is an overall picture of what it looks like. You can see, the double T's, and then below it, there's some catwalks, and really a large number of water tanks. Shortly after construction, someone saw a crack. That kind of motivated a whole bunch of, we need to do stuff. So they found this one big crack, and then a number of the other double T's had this fine diagonal cracking. So that obviously pressed the panic button. Temporary retrofit was installed, something to, emergency safety for that big one, and then the licensed design professional was retained to follow the 562 process, determine the cause, assess the implications, and developing the long-term repair. So this was initiated by that wide double crack. There was a temporary retrofit, but then the licensed design professional was retained. This is what it looked like, that main one, just to give you a sense of what the situation was. Obviously something, this is easy to say that there's a problem here, especially remember this is only a couple of years after construction, or shortly after construction. I'm not even sure if it was that long. First step, preliminary evaluation. So the preliminary evaluation, the licensed design professional did a visual review, collected all the relative information, and then basically decided that, hey, yeah, this is an issue. We need to do a structural evaluation, and very quickly rolled into a structural evaluation. And that was more of an in-depth investigation where they looked at the geometry, material strengths, reinforcement sizes. As part of that, so this is just part of the preliminary evaluation. This is, this cross section was developed based upon, to explain what was going on based upon the initial information they had. And they did, the visual walkthrough, use binoculars and whatever accessible areas. And they said, yeah, there's a problem. Go back, figure out what the design basis code is. So this was all documented. And it's interesting, one of the interesting things is this was only shortly after construction, but the original building code is based upon the building code that was applicable during the design. Even during this relatively short time, there's been this is replaced just by the timing work. There was a new current building code. So even new structures can have a different current building code and original building code. So it's not something that just applies to things that are 30 or 40 or 50 years old. It can also apply to new current structures. Adopted IEBC, and then also 562 was used. Did some calculations. Here's the demands. Most importantly, one of the things they did as part of the structural assessment was some non-destructive testing. And what they found was in the members, I'm not sure if it was all of them or just the ones that were cracked, they found that the DAP reinforcement was there, but then the welted wire reinforcement that was supposed to start at basically the beginning of the double T was actually shifted, and it didn't start till about 6 feet from the end of the member. So there was this 3 or 4 foot span that did not have any vertical shear reinforcement. So obviously this needed further investigation, and this is where I'm starting to go through things quickly. They started running through the calcs, seeing what the demand was, and they found that, hey, the capacity was only 49.5 kips without any steel, but the demand was 53 kips. So, and then, even if you divide, then you're really supposed to divide that by 2 to get your unreinforced capacity. So obviously, based upon these calculations, they figured out what the issue was. It was the missing steel, so that the double T's at this section didn't have sufficient capacity. Provided them with a report describing everything and looked at 4 different options. One of them, removal and replacement. Quick turnaround, really costly, but very disruptive. Looked at reinforced concrete jackets. Good compatibility, maintenance is low, but very labor intensive, very disruptive. A lot of dust and debris, going to be a big problem. Third option, steel plates. So, some ways easier than a concrete blockout. It's faster, but it's still going to be labor intensive, still going to be disruptive. You're going to have to work with these fairly large plates. And then more importantly, corrosion potential. You have to figure out a way to deal with corrosion of the steel. And then the final option was looking at CFRP and due to the simplicity for its installation, relatively still disruptive, but relatively less disruptive. That was a decision that was went for. They looked at, fire temporary conditions, if it had, if it was a candidate for external reinforcing, seemed to be was, strengthening can be used, did some checks, then they designed it by 440.2. And again, quickly going through this, don't kind of want to read all these equations to you, that bore me as well as you. It ended up with, this would work. We need one ply of 12 inches wide at 16 inches using a UWrap. So put the construction documents together. That's kind of what this looks like. Injecting the crack, getting all the right prep. And these are some pictures of the actually installation process. Looks like they actually they didn't do 12 and 16. They just did a continuous wrap. But they did provide an acrylic, UWrap on it, acrylic protective coating, kind of protect it going forward. QC was done, review of all the materials and metals, the delegated design, qualifications during the process. And then the important thing for this, bond was going to be critical, so they definitely did bond testing, verify, that the FRP was well bonded to the concrete. And then some closeout documents, what the maintenance requirement provided in the record documents. So I know that was really quick. I encourage you to go through that, trying to hit the highlights of that, fairly intense example of what's going on. But it's a good way of thinking about it. You can try to demonstrate how 562 was applied to that situation. So just to summarize, to kind of bring this to the end, here's the list of the steps. You need to do site visit, preliminary evaluation, design basics code, your more detailed evaluation, the design and detailing, specifying the material requirements from both a structural viewpoint and a durability viewpoint. Get your construction documents together that communicate all this to the contractor, develop your quality assurance program, and at the end of the day, submit this to the owner. Not the first part unique to repair. A lot of the second part, very familiar to someone who's done new design structures as well. The results are different. What's communicated different things. Emphasis maybe on different things, but conceptually it's still kind of the same process, except there's a long, much more of a different portion at the beginning to make sure you understand the structure, make you understand the aspect, and then kind of go forward from there. So again, a plug for, wanted to mention this guide that exists. This is what it looks like. It's where we got the example. If you're, you don't understand, you want a further in-depth detail of how the code works and how it was applied to real projects, it is a good resource that is available from ACI. And then I'm just going to skip through these because they're a list of other references that are available in ACI. And thank you very much. And I think at this point, if there are any questions, Katie, you can help me out with that.
Yes, thank you, Kyle. So our first question is if you could please elaborate on the limitations of acrylic bonding material in true structural repairs compared to epoxy.
That's a good question, and I honestly don't know the answer to that off the top of my head. I'm not a big bonding agent user, so I just know that there are things depending upon the opening time. Sometimes you need to let them. Some of these bonding agents you need to set first, but then they can only be a certain age. Become once they get too old, they set up and they're no longer bonding. But to talk about the difference between epoxy versus acrylic is not something I can do off the top of my head.
Okay. Our next question is, could you comment on the impact of elastic service load stress on steel corrosion rate, and in what portions of a beam, column, and slab structure Stress-enhanced corrosion may amplify overall corrosion development due to other factors.
Okay, that's another interesting question. So, in my opinion, the corrosion is really dominated by the environmental exposure, the presence of chlorides or carbonation. And my understanding is, for your normal black steel, stress, for the most part, stress corrosion is not going to make a huge difference. There's a lot more variability in terms of the exposure conditions as well. Just the amount of chloride that's getting there and what's that doing to it, rather than variations in stress. So I'm not saying that's not a thing, but I'm saying, if it's more important to think about keeping, having a good protection system, so you have your concrete that's embedded, your conventional reinforcing steel is embedded in concrete that can provide that high pH area and provide that protection. Higher stress rate areas do exist. I'm not saying that's not going to be contribution, but to me it's more of a secondary effect. And I don't know if that was the second part to that question that I haven't answered, but I think that's kind of my thoughts on that issue.
Okay. Our next question is, does the 150 psi pull-off test requirement imply a V sub U of 75 psi?
I believe the idea of 150 is it's a safety factor of like 2.5, which brings it down to 60. That's the intention. My math is not there.
Okay, and our final question for this afternoon. Surface repairs often need maintenance and periodic replacement to extend service life, such as waterproofing sealers. How should that be communicated to the owner or user groups so that repairs will not fail prematurely?
Communication is a big thing. One of the durability chapter, one of the things you need to consider, it talks about considering the maintenance program. That's not something that needs to be established as part of a discussion with the owner. What do they normally do? And that's where you can say, well, this is something, ways that we would recommend to improve that maintenance program to get better performance. But that's one aspect of it. Ideally you have a good relationship with them, during this process to be able to say that to them so that they're open to that. There's also, as part of the project closeout documents, depending upon what your contract is, I'm not, one of the things that we like to do when we can is provide them guidance to future maintenance in that situation. And that can either be, I have developed project specific or site specific maintenance programs, but obviously that has a cost implication that you need to communicate to the owner. And if they're open to that, that's great. And sometimes they've just spent, millions of dollars repairing it. They need to know, well, how can we do that? How could we not get in this situation in the immediate future? But alternatively, what I've done, there are a lot of industry documents. I know the National Parking Association, for example, has a whole guide on maintenance of parking structures. Can't remember who publishes it, but I know there's a similar one for bridge maintenance and things like that. So I've, at that point, you kind of point them in that direction to, at the end of the project, say, okay, you've now got your, shiny new structure back after we've done all the repairs. Here's an idea of what you should be, here's an implementation, some guidance for what you should be expecting for maintenance.
Okay, thank you so much, Kyle, for spending your afternoon with us and sharing your information with our attendees. So this does conclude our 4-part webinar series on 562. As you can see, we have some upcoming webinars on curing, seismic design, and cold weather concrete. ACI does offer our webinars in an on-demand format, so if you miss something, they are recorded and available in an on-demand fashion. That does conclude today's presentation. We hope you will choose to join us for future learning opportunities. Thank you.